Hi, my name is Stephen Price, and I'm a PhD student in the Computer Science Department at WPI. Today, I'm presenting my research on using machine learning to optimize the manufacturing processes of wire arc directed energy deposition, or wire arc DED. So today, the research that I'm presenting on is a new field of additive manufacturing that is much like 3D printing, however, it's using metal instead of plastic filament. And so this is a fairly new technique, and there's a lot of information that we still need to learn about optimizing the actual process. This includes how fast you're actually moving the robotic arm, how fast you're depositing material, and even what types of materials you're using. And so we sought to use machine learning so that we could improve this and make it a more efficient and sustainable process. So for a little background on this technique itself, it's specifically designed for building large metal plates such as like the outsides of ships or planes. And as you can see on the left, the initial print is a quite rough edges so that it can actually print those large sections, which then needs to be refined down. However, the actual efficiency and sustainability of this project is quite based on how much you actually have to refine it down. So as a result, you want to make sure that the optimal, or that the parameters used to print these structures is important, or is very perfectly decided, as well as so that you don't have any structural integrity issues. Now, so our approach for this was we printed a lot of different single layer test tracks so that we could evaluate the width of them, the height of them, the surface curves, as well as how consistent they are from start to finish, which it looked like this, where we have a series of, like a steel plate with a series of single layer tracks on it, and each of these corresponded to a different processing parameter condition set. And so then we used a 3D scanner to extract the surface profile so that we could develop an algorithm to actually measure these specific features that we were looking at. And so this was an example of one of the surface profiles of all of these different ones. And specifically, we evaluated the middle 50% so that there wasn't any issues with the start or finish of it. And then we measured the width, the height, and the variance of both of these. So then one of the next things that we did to actually improve the model performance was feature engineering. The initial materials that we were using was just a categorical variable, so for example, 4140 steel. However, in this case, the model couldn't actually learn from some of the chemical compositions of it, so it wasn't getting as much information as it necessarily could. In addition, it meant that the model could only be applied to the specific materials that were included in the training set. However, by doing feature engineering, in which we turned the specific model, or the specific material, into a set of continuous values, then we could improve the information available, and we could ensure that this model could actually be applied to new materials, even those that weren't included in the training set. And so for the actual models that we used, we had 4 different architectures that we implemented: linear, nonlinear, ensemble, and neural networks. This was so that we could understand more about the data, if certain models perform better than others, as well as a broader search to have the optimal performance. And so within these, we ended up finding out that polynomial regression performed even better than the neural networks or some of the more advanced ensemble networks for width and height, scoring an R-squared of 0.976 for width and 0.994 for height. And so this was a very high performing model for these. Width variance and height variance didn't perform as well, and they required a more complex model. So the best one was Random Forest, a ensemble network, in which they performed 0.784 and 0.669 respectively. So we think that there were some other factors involved, such as the cooling rate and some more material properties that were resulting in a less predictable thing that we plan on putting more research into in the future. So some of the conclusions of this project is, throughout this study, we collected the largest data set that has been collected for this specific problem. Other projects have used machine learning to predict these conditions, although they were using data sets between about 15 and 40 samples. Ours was 550, so we have a lot more information to go off. In addition, it was the first data set that actually considered multiple materials. So we had 5 wires, which was the deposited material, and 4 substrates, which was the base they were printed on, that we were actually evaluating in this. Additionally, we have the highest performing models on an external validation set. And so some of the future works that we're doing is looking at seeing how we can increase the information available to these models. So not just including the chemical properties, but also the physical properties, such as their melting points, their viscosity, so that we can give as much information to a model to learn and have a more accurate prediction. Additionally, we're looking at moving beyond just width and height to have more specific characterizations, such as the overall curve, the toe angle, and a couple other factors that we can use to actually develop 3D models so that this can be visualized rather than just looking at a set of numbers. Thank you for listening.